Hi, everybody. Thank you for attending From the Cloud to the Kernel, Powering Observability with eBPF. My name is Lawrence Gadban, and I'm a field engineer here at solo.io.
And I'm Eitan Yarmush. I'm an architect here at solo.io.
And this is a quick overview of what we will be talking about today. So first, we're going to lay the groundwork and kind of discuss what eBPF actually is. Then we'll be discussing what is BumbleBee and how it helps with eBPF. And then lastly, we'll see a hands-on demo. So to start off with, what is eBPF? eBPF stands for Extended Berkeley Packet Filter, which is an evolution of the original or classic BPF or classic Berkeley Packet Filter, which if you've ever used the tool TCP dump, that was based on classic BPF. So what it really does is allow you to do things like, say you're using TCP dump and you want to record some traffic, some network traffic from TCP traffic from one IP address to another. What you really are doing is writing a packet filter, and that's what classic BPF allowed you to do. Extended Berkeley Packet Filter is kind of the evolution of that, which enables all sorts of really interesting technologies to come about. A quick note is that eBPF and Bpf will be used interchangeably going forward. A lot of the pioneers of eBPF at this point have kind of started saying that eBPF is no longer an acronym, it's a technology. And since kind of eBPF has taken over, Bbpf is essentially can be used instead of eBPF at this point. As I mentioned, it's a Linux technology, and it allows you to run custom programs sandboxed in the kernel. It's really useful for being able to add custom functionality that otherwise would be impossible without changing the kernel and waiting months or years for that functionality to be available throughout widely available distributions. The programs that are written in eBPF are event-based, and what you can do is attach your program to various hook points that then will be triggered whenever those events are hit. So one example is something that's called a kprobe. A kprobe program is a program that's attached to essentially any kernel function. And then whenever that function is called, your BPF program that's attached to it will be executed. Another really important part about BPF programs is that they are verified to be safe. What that means is that there is a verifier that lives in the kernel. When you load a BPF program in, it will be verified that it won't crash the kernel. It's guaranteed to return. In other words, you can't write infinite loops. There's only specific sections of memory that are available to programs, and so on. So really, you get a guarantee that the programs that are being loaded into the kernel are safe. And this gives you a lot of confidence going forward because, before BPF, you could do things like write kernel modules, which if there is a bad kernel module, it could bring down your entire system. BPF works around that by verifying the programs before they are accepted. So an actual eBPF program, let's talk about that for a little bit. The program itself is, as outlined here, a sequence of 64-bit instructions that comes from kind of the unofficial eBPF docs, which are linked. Essentially, it's a sequence of bytecode or assembly, and Bbpf has its own instruction set. So that assembly, that bytecode, it is its own kind of assembly. That bytecode is then interpreted in kernel. There's an in-kernel virtual machine which can understand those instructions and actually execute the program. That being said, on most architectures, that bytecode will actually be just in time compiled. And that means that the bytecode, eBPF bytecode, will then be compiled into native machine code, which means that an eBPF program on most architectures can run just as fast as native code, which is really important for when you're trying to do processing, several events in the kernel. And kind of lastly, the actual BPF programs are typically written in a C-like, basically in C-like code. And then when you do that compilation step to assembly or bytecode, you'll use Clang or the LLVM toolset to compile your C-like code into that eBPF assembly. As far as writing eBPF programs go, there are several frameworks or libraries out there that help with this. BCC, or the BPF compiler collection, is kind of the original one. There's tons and tons of tools and examples using BCC. And essentially what you're doing is it's a front end with Python or Lua that will take Bbpf code in that C-like format and then use Python to help provide the front end. And then you will deploy your scripts or your programs. And then on the machines that you expect them to run, Python will use, the Python front end will actually call the LLVM toolset to compile on the hosts. So that means that you have to distribute, you can only run these programs on hosts that have LLVM, or you're shipping it with BCC. So it's really useful and really quick to get started, but you do have some, there are some implications for the host that you want to run on. Libbpf, which is second, is kind of a more modern take on that, which it tries to abstract away the actual functionality that needs to be provided by a library, and it gives you kind of a generic library that you can use in order to make all the system calls and so on that are necessary for running your Bpf program. There's also a really important part of Libbpf, which is that second line there, which talks about Bbpf portability using BTF, which stands for Bpf type format, and co-re or compile runs run everywhere. Kind of the goal here is that with the existing model, when you are using eBPF, if you compile only for a specific version, that means that your code can only run on a specific version of the kernel. That means that it's hard to distribute these programs to be able to run on more than one host. And so by using portability and co-re and BTF and so on, Libbpf enables you to write programs that can be used on multiple versions of the kernel, kind of really opens up the opportunity for distribution of those programs. We also call it Bpf Trace, which is a kind of higher level scripting type language that will allow you to utilize Bbpf, but not actually write the code directly. So kind of at a high level, what it looks like is you write some eBPF code in C, in a C-like format, and then you compile that using Clang, and you end up with an ELF file, which if you're familiar with Linux is kind of the standard execution binary format. You get an ELF file that represents your eBPF programs in that eBPF assembly or bytecode. And then when you actually want to run that Bbpf program contains kind of all the data that you need to, for example, create maps, which is the data structure that eBPF uses to where your programs can write data to, which can then be retrieved later by, say, your user space component. So you'll create maps. Your loader will create maps based off the definitions in that file. You'll also actually load the programs itself into the kernel. And then you have to attach it, right? So in this example on the left, there are some kernel functions that we may want to attach to. In this case, we want to attach the TCP v4 connect function. We'll go ahead and attach our program to that kernel function. In other words, this is a kprobe. And then every time that kernel function is called, that event will essentially trigger our program, which will get the more or less the data that the connect function received. So we can do some inspection or whatever there, update our map, and then whatever our actual program needs to do, say we just want to output some data, output some metrics, we can read from the map that contains that data, and that's now available in user space by the loader. So when you want to write these programs, at least kind of the standard way is you have a kernel space, which is the Bbpf code, and then you have a user space component. This is kind of an example we won't go too much into, but this is kind of a sample of what the code could look like. So here on the left is the Bbpf map. And this is really, again, as we mentioned a little bit earlier, this is really a data structure that's used by the program to say load data that can be retrieved by user space, or maybe you need to pass it to another Bbpf program. But either way, this is what it kind of looks like, where you're defining a struct in C, and then there are some special Bbpf conventions around that. On the right is the actual Bbpf code that will, in this case, this is what's counting TCP v4 connect function calls. So really, this is essentially taking the address that we're seeing in the connect and adding that to our map so that we can track those connection counts essentially. This is the user space of it. We won't go into the details here, but really what this is trying to show is that writing the Bbpf code is not enough. You also need to, in user space, load that, attach it, run it, and then clean up when you're done. And on the right side, what this is showing is that you need to be able to take that data out of the map. So this is a bunch of code here, but really what it's doing is writing out whatever. So in this case, we just want to output some data of the counts of connections. And on this, what we're doing here is we're printing out kind of a nice column formatted table, and then we're actually using a helper method to actually read the data from the map. In other words, there's a lot of work that you have to do on both sides to make a current Bbpf program work correctly. And with that, BumbleBee intends to help out. So I'm going to pass it over to Eitan to talk about BumbleBee.
So I don't know about y'all, but that was a lot of information. And I think that's the point. eBPF is an incredibly dense technology. It's very powerful, but can also be hard to jump into. And so that's why we created BumbleBee here at Solo. BumbleBee helps to build, run, and distribute eBPF programs using OCI images. It allows you to focus on writing eBPF code while taking care of the user space components, automatically exposing your data as metrics or logs. So let's break that sentence down really quick. So BumbleBee helps to build, run, and distribute eBPF programs using OCI images. So what is an OCI image? An OCI image is essentially a Docker image. So when we thought about building BumbleBee, we took a lot of inspiration from Docker because we feel that the user experience there is really great. Essentially, you build an entire application locally, push it to a registry, and then can run it from pretty much anywhere else. So we thought, why can't we do that with eBPF? And it turns out using the Open Container Initiative spec, we can. So, and we'll talk about later a bit more how this works, but essentially we allow you to build your eBPF programs in one place, store them in a registry, and then run them somewhere else. Part two, it allows you to focus on writing eBPF code while taking care of the user space components. Again, Lawrence went into more detail earlier about the different aspects of an eBPF program. And we thought to ourselves, how can we simplify that? What pieces can we abstract away to focus on the important part, which is getting the data out of the kernel and into a space that can be interpreted. And so by allowing users to focus on the kernel code, we take care of user space components and automatically expose that data as either metrics or logs. So we also allow you to write libbpf compatible Bpf code and only that. So again, no need to focus on user space code, and the build environment is completely containerized. So you don't need to worry about running in a specific version of Linux with all the specific depths and everything. The LLVM toolchain can be complicated. We take that away. And then third part, again, the OCI images easily push, pull, and run those programs from OCI compliant registries. There are many of those out there today. So how does building with BumbleBee work? Well, as mentioned, we create a pre-built containerized build environment. So we take, LLVM, Clang, that whole tool chain, as well as the BPF headers and all the information that is needed to compile your program into Bpf code. And that is stored in our registry at GitHub registry /soloio/bumblebee/builder. This particular release is from 0.10, but we will release a new version of it with each version of BumbleBee. And when you run bbuild, as we'll talk about in a second, it'll automatically use that image. So how does bbuild work? Well, bbuild, we modeled it as, again, after Docker build. So we thought, what's the simplest experience to build a Bpf program such that it can be packaged and saved to a registry? Well, here comes bbuild. So we pass in bpf.c, so that's the program that we're trying to compile, and then in the tag. And the tag, just like a Docker image, is where this will be stored. So we build the Bpf code into an ELF file. So we take our bpf.c, put it into our Docker container, compile it, which outputs it into a bpf.o. So that's our object file. That's the thing that will actually get run. And then we take that object file and package it up into an OCI compliant package so that it can be saved to a registry later. And we can do that with bpush. So what does bpush do? Again, very similar to Docker push. You can take your built image and send it to any OCI compliant registry. Certain registries will only accept Docker images. Off the top of my head, Docker Hub will only accept Docker images. but an example of others that are more that will accept other images are GCR or the new artifact registry, as well as Harbor or any local registry. Or the GitHub registry as well, as you can see here in the example. So now that we have compiled our eBPF program into our OCI compliant image, we're going to push that to our BumbleBee repo. So once we've pushed it, we can actually go ahead and run it. And in this example, it shows it running from the same computer that we have built it. But part of the magic here is that it can be from anywhere. It can be from a Kubernetes cluster halfway across the world. The only limitation is that it needs to have a newer version of the Linux kernel with BTF enabled. And we'll go into more detail about that later. So how does it actually work when you run a BumbleBee program? Well, as I said, we abstract the user space code. So what are we actually doing? Well, essentially, when you run the program, we'll take that packaged up BPF program and use some very specific metadata from it to load that BPF program into the kernel, create some maps that have been specified, and then take data out of those maps. So once the BPF program is running, we watch those desired maps and output that data as either logs or metrics. And we do this again by certain metadata provided to us in the kernel program itself. So every time you run one of these programs, there's no user space necessary. You just do B, run, and that's it.
So Eitan just covered how the workflow works when you're using BumbleBee. Now let's take a look at how you actually write the programs with BumbleBee, how you actually write your Bbpf programs. So as we looked at earlier in the talk, when you're writing a traditional Bbpf program, you have to write the kernel space, the actual Bbpf code, as well as the user space. With the BumbleBee abstractions, the user space goes away. And so really you just need to only write the Bbpf code, which again is doing things like defining what maps you need to use for your actual program logic, and then updating those maps with the data from your events that are firing based on whatever hook points you have attached to. So here on the left, we can see very similar to the previous map we looked at, where we're defining a Bbpf map. In this case, you can see that the type here, this is the type of map that we're creating. And in this case, we're creating a hash map. So Bpf map type hash. And this is what will be used. So the example that we've been using this point is, tracking connections and counting connections. So this map will be used to count each connection that happens from the kernel to a given address. We'll keep track of that and count it. And we're using kind of a struct here called dimensions_t to track the source and destination address. And then on the right, this is the actual Bbpf code that's updating the map based off the data that we're getting. So again, this will essentially fire whenever the TCP connect function that we've attached to is called. So in other words, when a connection is established in the kernel, we will get access to, for example, what address it's connecting to. And then this code is basically updating the map with the address and then updating the count for a given address. All the user space code goes away. And the way that works is that we have this struct for the map and the struct that keeps track of the actual source and destination address. We can utilize this data, and we can also reuse the Bpf type format that we mentioned earlier. We can reutilize that to understand the type of data that you're storing in your maps. And so in this case, we have a hash map that uses the key for that is this dimension struct that we just looked at with the destination and source address. What that means is that we can understand the type of this dynamically because it's built into the ELF file, the output file. And we understand that there is a field that's the destination address, and there's a field that's the source address. And these are IPv4 addresses. And so this type here, this IPv4 address is actually something that we have built into our build container, which kind of gives well-known types to certain to specific types of data. And this is saying that the destination and source address is an IPv4 address. So on the BumbleBee side, when we actually run it, we can then interpret this data that's being passed in the map in the key as an IPv4 address. And so we'll go ahead and dynamically render out this table here with the data in the correct format. So we have IPv4 addresses for the destination and source address. Another interesting thing that we can do is, if you were looking closely at the example earlier, when you define a Bbpf map, you typically are going to use this section functionality to determine which section in the ELF file your code gets output to. And so the .maps is kind of a convention that says it's a Bbpf map. What we've done is added on to that, and we've added some functionality where you can see this .maps.counter suffix. That also allows us to do some cool stuff. So in this case, we're dynamically determining that the value of this hash map is a counter, and we can dynamically track the value here, which is corresponding to the value field in your hash map, and we can automatically output that and update it based off of just by you adding this .maps.counter. And so it really allows you to kind of write your Bbpf code, and then basically using some conventions, dynamically get a program that can run it, and also can add some smarts to, say, your metrics and output. Speaking of metrics, we also can take that data and output it as Prometheus metrics by default. So going back really quickly, since this is a counter, we're also saying that we want to not only output it when we run it here on the screen, but we also want to treat this as a counter in Prometheus style metrics. So using that same example, we have an events hash, and in that we have labels for the destination address and the source address. And again, those are all determined dynamically just from the type of map and the section of maps that we're defining. And so, you can start thinking about how powerful this is, because you will get kernel-level Bbpf observability data, and just by using B as the runner, you will dynamically get the logs that we were just looking at, and you also will get Prometheus metrics. So with that, let's go ahead and take a hands-on look. I'm going to pass it back over to Eitan, and he'll provide us with a demo.
So without further ado, let's get started on this demo. So we've been talking a lot about BumbleBee, so let's actually see it in action. So the first thing we're going to do is we're going to install the latest version of BumbleBee. And to do that, we're going to use the install script. So I'm just going to quickly search my history through the install script, and we're just going to run that right here in the terminal. So as we see, I'm downloading the latest version. That's going to happen to be 0010 right now. So once I have that in my path, I can go ahead and export it to my path. So I'll do that now. And I'll do that in both of my windows. And it's important to know that when running BumbleBee, there are a couple of options for doing this, but it needs to be run with sudo. And the reason for that is that in order to increase the memory limit for the maps, you need to be running as root. So from now on, when we run these commands, we're going to be running as root. And I'll show you how to do that in just a second. So now that we have BumbleBee installed, let's go ahead and run it. So we're going to do sudo, and we're going to do b-help. Take a look at what we got. So if we run bhelp, you see that we've got a bunch of commands. And again, we're going for that Docker style user experience. So you'll see build, you'll see push, package, pull, all the goodies here. So what I'm going to go ahead and do is, very first thing, I'm going to use init. Now, what is init? Well, init is going to initialize a sample Bpf program for us so that we can go ahead and start writing it. So I'm going to go ahead and I'm going to say b, and in this case, I'm just going to use b because I don't need sudo. B init, and then it's going to run me through a bunch of interactive steps and starting my own new eBPF program. So what language do I want to use? In this case, it's going to be C. It's the only language they offer at the moment. And then for the sake of this demo, we're going to do a network-based app, but you can also choose file system here. And then do we want to use a ring buffer or a hash map? And now these are two examples of maps or the data structures that you can use to communicate between user space and kernel space with eBPF programs. And we're going to choose a hash map application right now. But the difference is essentially that a ring buffer you just throw objects into, so it's more like a queue functionally, and a hash map function is more like a typical map in, let's say, Go. And the last thing we have to pick is what kind of output do we want. So as we've been discussing, right, by the main purpose of BumbleBee is to run applications which surface metrics. And by doing that, we abstract, again, the user space code away. So we're just going to quickly decide what kind of metrics we want to expose from this program. In this case, we're going to pick counter. Now I just have to pick a file location. So I'm going to do SoloCon.c. Boom, successfully wrote our skeleton Bpf program. So let's go ahead and take a look at what that is. So I'm going to open up SoloCon.c. And when I open up SoloCon.c, I see a lot of information. So let's unpack all of this really quick. First of all, we've got our license, very important. Every eBPF program needs a license. Second, we've got our dimensions. Now these are the dimensions for our stats. Essentially, what information are going to be published with each statistic. So as you add more, you add them to this struct here. Then we have our map, which actually contains the data. So this is one of the neat things that BumbleBee has added, is this, you see here, .maps.counter. So typically in an eBPF program, when you specify something as a map, you put .maps. So in BumbleBee, we've added another thing, another layer on that. That's the type of output that you want from that map. So it could be .counter, .gauge, .log. Right? These are the different types of outputs. And the next thing is our kprobe itself. And in this case, it's going to be TCP v4, so those are IPv4 connections. And again, here we just have some boilerplate code to start off on the right foot. So we create a key for our dimension or our statistic, and then we initialize all the values that we need to actually emit a stat for each connection. Now, as much as this is a very powerful building block, for the sake of this demo, I have an example built and ready that I'm going to quickly swap over to, because it will also allow us to take a look at some of the powerful statistics that we can get with BumbleBee. So I'm going to open up here a program called tcpconnect.c. And this one is really just an extension of the earlier program that I show you, the SoloCon.c. Similarly, we have our dimensions here. Now, in this case, our dimensions are source address and destination address to show off essentially the ability to capture all traffic from one address to another, and that could be filtered down to a single address, or just to capture across all addresses and see where traffic is flowing in our network. And in a minute, we're going to get to show that off here. So similarly to the other one, we have our kprobe set up at the bottom. In this case, there's not just the probe on the entrance to the function, but also on the exit. And that allows us to capture more info about the actual probe itself. So now that we've taken a look at the program, we can actually go ahead and build it. So what does it mean to actually build this program? Well, to do that, let's go back to the terminal over here. So the first thing we're going to do is we're going to go and check out our command list again. So when you want to run one of these programs, the first thing you need to do is build it. So let's build it. So we're going to run sudo b build, and then we're going to see what build wants us to pass. So build wants two args, and the args that it needs are going to be the name of the file, so the program that you're building to, and then the tag. So exactly like Docker. So I'm going to pass in bbuild, and then I'm going to pass the name of the program that I want to build. So in this case, it's going to be tcpconnect.c, and then I'm going to pass the image, and in this case, it's going to be my image : latest. And this can be anything. Again, this can be a Docker image, right? This can be pushed to any registry. For the sake of this demo, I'm just going to push it to a local registry. So I'm going to call it my image latest. Apologies for the brief technical issue. Let's pick up right where we left off. So I'm just going to quickly build the image. And as we can see, we have successfully created our new image. So what does this actually do? Well, the first thing it does is it's going to write our image to TCP connect.io. So that's our object file that we're actually writing to. And you can inspect that if you want to see more details about the program. But the other thing it's going to do is create our latest image. So it's going to take our eBPF program and put it in an OCI image. So now that we've done that, we can actually go ahead and list all of our images. We'll see that, look at that, we've got our image is listed. So we can see that we have built an image for Linux. This is our operating system version, so it's our kernel version 5.10, and then our architecture. We support ARM, and yeah, so those are the different options that you would see there. So now that I can see our image, let's go ahead and run it. So in order to run it now, all we have to do is do b run and pass in our image. That's it. And now we're greeted with this really cool terminal UI. Thank you to Lawrence for doing a ton of the work on this. So now that we've got our terminal UI, let's go ahead and see what it can do. So let's do a quick curl to hpbin.org. And we see that it shows up right there. So what's actually happening? So when we make our curl to hpbin.org, our program is recording so the program that we ran using B is recording the source address and destination address to a metric, to a hash map, which then BumbleBee is picking up and putting in a metric. Or right now it's printing it to the screen. However, in a minute, we'll be able to see that it is also pushing it to a metric. So in the case of the TCP Connect program, we're pushing it to a hash map and a ring just to show the difference. So the hash map tracks the value over time, whereas the ring is, like I said, it's like a queue or a log, and you just see all of the individual entries. So the destination addresses here are the different IPs that hpbin.org has resolved to. And so the last thing I'm going to show off is just going to be seeing these metrics using Prometheus. So I'm going to run a local Prometheus server here. I'm going to jump, and then I'm going to curl hpbin a few more times just to get some data, because we really want to see what this looks like. So I'm just going to do that a few times. Alrighty, and then I'm going to jump over to our browser and I'm going to reload with Prometheus. And as you can see here, boom, I've already got it. I've got our metrics. They're flowing through all the way to Prometheus from BumbleBee. And as you can see here, I can actually track on individual destination addresses and see all using BumbleBee. So that's the power of the tool that we created. We hope you enjoyed the demo. As mentioned, BumbleBee is a totally open source project. Go check it out. We'd love to hear your feedback. We love PRs. We love comments. And thank you guys so much for listening to our talk.
Yes, thanks everyone. So we'll be hanging out, taking any questions if you have them. If not, as Eitan said, go check out BumbleBee, open issues, lead PRs. Yeah, thanks everyone.